All right, this is a quick video to give you an introduction to the splitter merger box. This is for the Active 2 and Active 3 systems by Biosemi. So this typically is used for the trigger port, but it can be used for the analog input box as well. Let me just give you a quick run through on how this is arranged. So you have 16 BNC inputs, as you'll recall if you're a user of the Biosemi system. The trigger port on the Active 2 or Active 3 system has 16 input bits. So this bottom row, or this bottom label here, and this connector carry all 16 of these BNC signals. But it also is possible to route signals from a 37-pin input port, which is what the typical Biosemi trigger cable connects to, or one of two 25-pin ports on the sides of the box. So you have multiple options for routing signals in, out, and out of the box. And as I said, it can be used for the trigger port or the analog input box, because both essentially have the same ground and signal routings on the 37-pin input connectors. So to illustrate a few of the features, the box has these BNC inputs, but it's annoying to have to short all of those. We have some shorting BNC connectors here, but there are switches here as well. So if I want to turn off a group of 4, I can just turn off the switch next to it. So this down position is off and the up position is on. So here I have the third row on, but I have BNC shorts on these 3, so only the first of those is available for input. So if you want to hold everything low, you can simply use the switches plus some BNC shorts, and then leave one or more than one input available for your device to connect to. Okay, so now we have the splitter merger box connected via its 1 to 16 output port. This 37-pin cable goes to the trigger input of the Active 3 system, which is on the back here. So this is a 37-pin female to male cable that connects to a male output on the box and a female input on the Biosemi trigger port. So I'll have all of my inputs on, and I'll remove all of these BNC shorts to be done with. So we have these 3 shorts here. Just to give you an idea how it works, I'm just going to walk through everything. So I'm going to run the Biosemi software. And here in Active View now, if I click Start, I should see some traces scrolling across the screen. And you'll see these colored lines at the bottom. These are the trigger inputs. They're all high right now because they're pulled up by pull-ups on each of the inputs. In other words, resistors that pull these inputs to a high state. Pulling an input high or low is the traditional practice in order to avoid them being in some middle state that's undefined. So they've been pulled high. And if I switch over to the About tab on Active View, you'll see that I'm in analog mode. In analog mode, these lines are displayed as colored lines. In decimal mode, they would be displayed as a numeric value on the input at the point at which there's a change. So let's look at it in analog mode first, and then I'll show you decimal mode. All right, so I'm in analog mode, and we can see we have a lot of high inputs. One way to utilize some of those inputs would, of course, be to use the Biosemi trigger cable, which is this cable. It is USB on one end, and it's a 37-pin parallel on the other end. So essentially inside here you have a microcontroller that converts the USB signal to parallel, which is what the Biosemi EEG and most EEG systems expect. I'm going to connect that trigger cable to the input. So you'll see that the first 8 inputs have all gone to 0. That's because at the moment, no signal is being sent over the USB trigger cable. So these 8 inputs, even though the switches are high, they're all held low by the trigger port, the trigger device itself. So if this were not connected, I could turn those inputs low on their own with the switches. But if I have the trigger cable connected and I have these switches on to enable that port, now I have the presentation software up and it's already set up to communicate to this trigger port. So if I click the button to test the port, then I'll see here I have a 255, which is a high state on the first 8 bits. It's strictly speaking bits 0 through 7, pins 1 through 8, but those 8 bits form a 255 when they're high. So if I were to say send a 1, then you can see I have this 1 bit high. Okay, so if I click send, and I send a 1, you can see that only bit 0, the first pin, is being raised. If I send a 2, then the second bit is being raised, 4, and so forth. So if I were to convert that to analog, or to decimal, rather, then I would see when I'm raising only a 1, it will come across as a 1. 2 as a 2, 4 as a 4, and so forth, all the way up to 255. And you can see that 255 is it's essentially interpreted as one number, even though it's a change in the state of multiple bits on the port. Now let's say we want to connect something in addition to the trigger port. So right now we have all of these pins, or all of these ports on. Let's try turning off one of them. So that leaves this row 3, pins 9, 10, 11, 12 on. But I only want to connect a signal to 9. So I'm just going to short 10, 11, and 12 with these little shorting jumpers. I'll connect my signal to 9. And this is just a 1 Hz square wave that will be coming from my signal generator. So now you can see that that 1 pin is being modulated at a rate of 1 up and down cycle per second. I can increase the rate here. That's 5 Hertz. And back down to 1, or let's go to 10. So there's 10 Hertz. You can see at 10 Hertz, you get about to the point at which the screen resolution makes it difficult to interpret these, mainly because at this rate, where the screen is undersampling the data significantly. But that doesn't mean that the data points are not accurately represented by the system. They are. It's just a matter of the display not being high enough resolution to be able to account for all of the changes on the port. So at 1 Hertz, I'm modulating just that 1 pin. If I wanted to move that around, my other options would be any of these other input pins on that row, or I could raise these pins and put my signal on 16. Now you can see my signal is on 16, but I still have some of the other bits on that final row that are not shorted, so I can go just short them with the shorting jumpers. And that gives me full access to all of the pins on the trigger port as inputs. Now you can do pretty much the same thing with this on the analog input port by connecting the 1 to 16 cable to the analog input port instead of the trigger port, and then just view these as all inputs. You can, of course, then have other inputs on these other cables, but you would just treat this as the pathway to send signals between the in-sync cables and the analog input box, the AIB, for the Active 2 system.